Get this, AI that learns in real time. Like, imagine a Mars rover adapting to new terrain without sending data back to Earth.
Right.
It's pretty wild. It's no longer sci-fi. This is streaming deep reinforcement learning. And that's exactly what we're diving into today.
Absolutely.
Hit that like button, subscribe, because we're going deep into a research paper that's really cracking a major barrier in AI.
Yeah, that barrier has been making deep reinforcement learning work without huge amounts of stored data.
Okay.
Which is a game changer for devices with limited resources or applications where privacy is really key.
Okay, so traditional deep RL, I think I've got this right. It's like cramming for a test the night before. You need all that past material to do well.
Yeah.
But streaming RL is more like learning as you go, incorporating each new experience.
You got it.
Way more efficient.
Much more efficient. And this paper introduces these StreamX algorithms that perform comparably to the data-heavy methods while learning in real time. No more giant replay buffers or waiting forever for batch updates.
Color me intrigued. So what's the problem that this paper is trying to solve?
Well, for a long time, deep reinforcement learning needed to store massive amounts of past experience to be effective.
Okay.
And that made it impractical for a lot of real-world situations.
So that's why we haven't had those super smart, adaptable robots everyone's been dreaming of.
Exactly. Previous attempts at streaming deep RL were just too unstable. They would often fail to learn anything.
Really?
Yeah. This paper tackled this head-on. They call it the stream barrier.
Okay, so how did they crack this stream barrier?
Well, they developed a whole bunch of techniques that actually stabilize streaming learning, making it work with those complex neural networks.
Ooh, that sounds promising. Give me the details.
So one is called Sparse initialization. Imagine starting a neural network with most of its connections set to 0, like a map where only a few places are filled in.
So instead of having a jumbled mess of connections, it starts with a few key pathways.
Exactly.
And builds from there.
Exactly. That helps focus the learning process and avoids interference. Then there's eligibility traces. Think of it as a way to reward actions that led to success, even if they happened a while back.
Oh.
Like giving credit where credit is due, even if it takes a few steps to see the result.
That's clever. And what about that overshooting bounded gradient descent thing I saw in the paper? It sounds like a mouthful.
It is a mouthful. Think of it like cruise control for learning. It's a new optimizer that keeps the learning process from going off the rails by making sure updates are always within a safe range.
So it's like a safety net for the AI's learning process.
Yes.
What else?
Normalization.
Yeah.
Which is basically keeping the data within a consistent scale, like adjusting the volume on a speaker so you're not blown away by sudden loud bursts. It helps with stability and avoids any nasty surprises during learning.
All right, so they stabilized the learning.
Yeah.
But did it work? Did the AI actually learn anything?
That's where things get really interesting. They ran tests in a variety of environments like simulated robots and Atari games. And these StreamX algorithms learned fast. In many cases, they matched or even surpassed the performance of traditional methods.
Hold on, they learned just as quickly, sometimes even faster, without needing to hoard all that data.
Yeah.
That's a game changer. So these algorithms are like the David to traditional deep RL's Goliath, taking down the giant with speed and efficiency.
It's a great analogy. This research really challenges the assumption that AI needs mountains of data to be effective.
Okay, but I have to ask, how do these StreamX algorithms actually learn? It all sounds pretty magical.
Well, it's all about updating a neural network, which you can think of as like a complex mathematical function. In streaming deep RL, the input to that function could be, say, sensory data from the environment, and the output could be an action to take.
So the neural network is like the AI's brain, and the StreamX algorithms are shaping how it learns and adapts.
Exactly. And remember, these algorithms learn from each experience in real time without needing to store and revisit past experiences.
Right, the whole streaming thing.
Yeah.
But how does updating the neural network work with just one experience?
Well, it hinges on something called the TD error, which stands for temporal difference error. It's basically how surprised the AI is by what happens after it takes an action.
Okay, walk me through an example.
Sure. Let's say we have a self-driving car, and it decides to make a turn expecting a clear road. But suddenly, a pedestrian steps out into the crosswalk.
Yikes, that's definitely a surprise.
Right. That unexpected event creates a large TD error telling the algorithm, hey, your prediction of a clear road was wrong.
So the TD error is like a wake-up call, prompting the AI to adjust its understanding of the world.
Precisely. And those StreamX algorithms we talked about, they use this TD error to fine-tune the neural network, nudging it toward better grasp of the environment and how to act within it.
So it's a constant cycle of prediction, action, feedback, and adjustment. The AI is always learning and refining its model of the world based on each experience.
That's the elegance of streaming deep RL. It mirrors how we learn through continuous interaction with our surroundings.
That makes sense, but it still sounds complicated. Is there a simple way to think about how these algorithms work their magic?
Picture a sculptor slowly shaping a piece of clay. Each experience the AI has is like a gentle touch, subtly molding that clay over time. The TD error acts as a guide showing the sculptor where to add or remove material.
Okay, I'm following. So the AI is the sculptor, the neural network is the clay, and the StreamX algorithms are the tools and techniques.
Exactly. And like a master sculptor who creates a masterpiece through small, deliberate actions, these algorithms shape a powerful AI through a steady stream of experiences.
That's a great analogy. It brings me back to what we were talking about before, how these algorithms defy the need for huge amounts of data, which is something we usually associate with AI.
It's one of the most exciting aspects of this research. It proves that DeepRL doesn't have to be a data-hungry beast to be effective.
You mentioned earlier that these StreamX algorithms learned incredibly quickly. What were the specific findings?
Well, in their experiments, the researchers saw these algorithms learning as fast as, and in some cases, even faster than traditional methods that use those huge replay buffers.
Wait, so they're learning just as much, if not more, without needing to hoard all that data. How is that even possible?
It comes down to the techniques they used. Those stabilizing techniques like overshooting bounded gradient descent and normalization, they help the algorithms get the most out of each experience, wasting less effort and speeding up learning.
So it's not just about the quantity of data, but the quality of learning from each experience. It's like the difference between cramming for a test and deeply understanding the material.
You got it. And that's why this is so significant. We might be able to achieve truly intelligent AI without needing those massive data sets, which opens up a whole new realm of possibilities.
This is really making me rethink the potential of AI. But let's go back to that experiment with predicting electricity consumption. You mentioned the StreamTD algorithm could predict 25 hours into the future. How did they measure its accuracy?
They compared those predictions to the actual electricity consumption that happened during that 25-hour period. And what they found was impressive. The predictions were incredibly close to reality, proving the algorithm's ability to learn the complex dance of electricity demand.
So it wasn't just luck. It was the algorithm genuinely learning patterns and making accurate forecasts. That's incredible. It really showcases the potential of streaming deep RL to tackle real-world problems.
Absolutely. And this is just one application. Think about using these algorithms for other prediction tasks, like forecasting stock prices, predicting the weather, or even anticipating earthquakes.
The possibilities are truly mind-boggling. But we'd be remiss not to acknowledge the challenges that still lie ahead. Right, as exciting as all of this is, streaming deep RL is still a pretty new field. What are the big questions researchers are still trying to answer?
Well, one of the main challenges is to push that efficiency even further. Even though these algorithms are already learning quickly, there is always room for improvement. Researchers are always on the lookout for new techniques to squeeze even more learning out of each experience.
So it's like fine-tuning a race car, always looking for ways to shave off milliseconds and gain an edge.
Exactly. They want to make these algorithms the best learners they can be. Another big question is about the limits of streaming deep RL. Can it handle really complex, real-world problems, the ones with lots of variables and unpredictable situations?
Like, can it learn to reason, plan, and make decisions that require more abstract thinking? It's one thing to learn to play a video game, but it's another to navigate the real world.
Those are exactly the kinds of questions researchers are grappling with. They want to know if these algorithms can truly understand and interact with the world in a meaningful way.
It's like we've opened this door to a whole new way of thinking about AI, but we're just beginning to explore what's possible.
I think you're spot on. Streaming deep RL has the potential to bridge the gap between artificial and natural intelligence. It could allow machines to be much more fluid and dynamic in how they interact with the world.
And going back to what we talked about earlier, the fact that these algorithms can learn so well from limited experience really challenges our assumptions about AI. We thought it needed to be force-fed data, but maybe it just needed a way to learn more like we do.
That's a great point. We don't learn by passively absorbing information. We learn by doing, by experimenting, by messing up, and figuring out what works.
It's like that saying, experience is the best teacher. And these StreamX algorithms seem to get that. They learn through direct experience just like us.
And just like us, they learn from both their successes and their failures. That TD error we talked about, it's not about punishing mistakes. It's about using those mistakes to learn and improve.
So the AI is running its own experiments, constantly testing and refining its understanding of the world.
That's a fantastic way to put it. And this ability to learn from all kinds of feedback is what makes these algorithms so adaptable and resilient.
It's like they're constantly adjusting their internal compass, making sure they're always heading in the right direction.
And that adaptability is critical in the real world, where things rarely go as planned. Think about a self-driving car dealing with a sudden detour or a robot exploring a totally unmapped area.
These are situations where traditional AI, with its reliance on pre-programmed rules and mountains of data, would struggle.
But with streaming deep RL, the AI can adapt on the fly, using each new experience to figure things out.
It's almost like we're giving AI the tools to think for itself, to solve problems without needing a human to step in every time.
That's the ultimate goal, right? AI that can not only perform tasks, but truly understand the world and interact with it in a meaningful way.
This research feels like a big leap in that direction. It's like we've unlocked a new dimension of AI.
I agree. There's still work to do, but streaming deep RL has the potential to revolutionize AI and so many other fields.
I'm excited to see what kinds of applications come out of this. Imagine robots exploring new planets, personalized medical devices that adapt to each patient, and intelligent systems seamlessly woven into our everyday lives, all learning and evolving in real time without being held back by massive data storage.
It's a pretty amazing vision, and one that I think we can achieve.
Well, I don't know about you, but my mind is buzzing after this deep dive. It's inspiring to see how AI researchers are pushing the boundaries of what's possible.
I'm with you on that. It's a really exciting time to be following this field. Who knows what other breakthroughs are just around the corner.
And to all you listeners out there, keep exploring, keep asking questions, and keep diving deep into the world of knowledge. Until next time, stay curious.